These are their stories.
Yeah, these are so dun dun.
Right?
Or actually, should it be the sound of like 2 rocket engines igniting?
I can't replicate that. I'm sorry.
Yeah, I can't either. So
I think I did amazing with that.
oh boy.
My random bit of confidence.
Yeah. And is it okay to introduce you as Dr. Eric Smith?
Sure.
And we've got you written down as the James Webb Space Telescope program scientist from NASA headquarters.
That's right.
Okay.
Right.
Very cool. Yes. Got it. Yes. So well, you know, just with the intro, we kind of do like a quick introduction of ourselves, and then we introduce you, and then we just go straight into it. So it's literally like 30 seconds after we begin, we are underway, and the ride has begun. So, so we'll kind of
That's good.
Yeah, we'll kind of see how it goes today. So, should be really fun. This is just such a Sarah and I work up at Griffith Observatory, and we've had a lot of talks given by scientists and engineers about James Webb. So this has been something we've been looking forward to for a very long time.
Yep.
And very excited to see it moving forward. So
absolutely.
Yeah.
Actually, I was supposed to come out there and give the Friday science talk in January, but because the government was shut down, I couldn't go.
Oh my gosh, dude! Okay, sorry. I work on All.Space.
I work on All.Space as well. So
we almost met you in January.
Oops. I appear to have spilt a bit on my pants. It's all right.
You fiddle.
Who's so excited his water leapt out of its bottle.
Yeah, you saw that, didn't you? So
I think we're going to retry for September.
Oh, cool. Yeah, very awesome. So, also today is, if I remember right, today's like the official 2 years from today is when James Webb launches.
That's right. We have we're carrying the March 30, 2021 as the nominal LRD, launch readiness date.
Okay, cool. We'll definitely note that during the show today for those who don't watch on demand. Or those who don't watch live, that's their fault. So, and did I lose chat?
Oh
no, I just needed a refresh. Oh, apparently I kicked myself out of chat. I don't even know how this works. Oh, computers.
Right. If you want to focus on questions, I can be in host, so that way you can just focus on him.
Oops, I just closed tomorrow.
That's a good idea.
I'm not good at this. So
Good, I'll focus on
Jared,
that.
yeah, Jared, you stay in your notes, Sarah, you stay in the chat room. I like that a lot.
okay, cool. Sounds good.
Yeah.
So,
Got you, bro.
whoa, we have YouTube and Discord in here today. What's up, y'all? How we doing?
You got Twitch too.
Yeah, we have Twitch. Shout out to all the internets out there. We're playing fast and loose today, I tell you. So,
Somebody pitch in from the dark web.
those of you running tour, how's it going? Anyways, all right, that's enough of that. This is falling apart, and it's not even 11 o'clock yet. So, Eric, are you back east?
Yes, I am. Yeah.
All right, very cool.
I'm actually in a place about not quite halfway between Baltimore and Washington called Ellicott City.
Okay.
Suburb. 8 o'clock on the dial from downtown Baltimore.
All right. That's a way to do it. So,
Yeah. I'm not sure if that's something on our side. I don't know what we can do there. Yeah, mute.
oh, okay.
Yeah, right.
Ben's doing the technical work right
Yep.
now, and we were able to hear him very well. So, and then. That's the way it goes. So.
It mentioned on your bio that you were on Hubble, but I didn't get to dig too much deeper into that. What were you doing with Hubble?
I worked on Hubble twice during my career. When I first started at NASA,
Okay.
was called the Data Archive and Distribution System, DADS. It was the software that handled the data once it came down from the satellite. And then
Gotcha.
when I went down to NASA headquarters, I was the program scientist for Hubble for a while and also got to work on the final servicing mission there. So that was very exciting.
That is awesome.
That's so cool. And you also worked on the Ultraviolet Imaging Telescope, which flew on 2 shuttle missions as well. So,
Right.
that's really holy moly. So,
that was a fun effort because it was much more hands-on. We actually got to run the telescope from an operations center at the Marshall Space Flight Center, and it was just like, because it was a shuttle, it is a manned mission, so you're wearing the headsets, you're on the loops, hearing what people are saying, so that was fun.
yeah, that's really cool. No, move the telescope to the left. So I'm sure there's something to be said about working with test pilots and military guys with that. So.
It's a whole different kind of chutzpah than scientists.
Oh, that's great. I love it. So, yeah, I know there's when up at Griffith, when we have scientists come in and then astronauts come in to talk, it's like two completely different types of preparation and how should I say,
even hoopla,
commiseration,
yeah.
I suppose.
Yeah.
So it's entertaining to say the least. So.
The scientists walk in and nobody, they just walk in the door.
Yeah,
That's lovely.
That's like so like upsetting too.
I
it's
know,
so
there's
cool.
that, but
there's like tons of awesome scientists out there, and
absolutely. But it's just as a person who.
Well, we don't wear the lab coats. Like they get to wear the blue jumpsuits. We don't wear the lab coats.
Maybe we should start wearing lab coats out and about. So,
or at least tweed jackets with the elbow protectors.
Yes,
Some identifier.
That helps very well. So, but they have to be fashionable tweed jackets.
Yes.
So, none of this. We've got to step that up. So,
yeah.
So,
imagine like English riding coats.
Yeah. Like we got to think like
really fitted.
Like what would we wear to the Met?
Yeah.
Kind of.
Yeah.
That's how it would work. So, something like that. So, Vax Headroom, our resident. What titles have we given Vax? Vax has a multitude of titles.
Resident Moonabomber?
Yes, the Moonabomber, because he worked on L Cross.
Okay.
So which ran right into the moon. He says he has a blue lab coat. So that's cool. So that's pretty neat. Why can't astronomers wear flight suits? I bet if you flew on Sophia, you could wear a flight suit and get away with it.
I think you would have to.
Yeah.
I bet you
have to do that.
Couldn't get away without it.
You have that, and you can carry a bag and like walk in slow motion up to it. So
yes.
Play that one Berlin song from Top Gun. I can't remember the name of it.
It was Berlin? Really?
Yeah, I think it was Berlin, wasn't it?
Take My Breath Away?
Yes, that one. Yeah, you could do that.
No, that's
both a metaphor for like this is going to be exciting, and also like we're at 55,000 feet.
No, that's the love song. You want Highway to the Danger Zone.
Well, like it's not really like Danger Zone status. So.
I don't know. You got a 747 with the side ripped out?
Yeah, but it works. So that's the thing.
So do F-14s.
Fair enough. What does this show become?
Awesome as always.
We're 6 minutes out now. So.
If there's any nerdliness that you would like to contribute, Eric,
yeah, feel free. Throw it in.
Feel free.
Okay. Yeah, I haven't had a chance to fly on Sophia yet myself, but it would be an interesting ride, that's for sure.
Yes.
It's much more like going observing at a ground-based observatory. You know, it's a little bit of, it's not terribly glamorous. You're just sitting there looking at your station, watching your data come down. But sometimes, at least it's hands-on in a way that when you're doing space stuff, it comes to you in your computer in your house. And so you lose a little bit of the romance that going up to the telescope brought to you. That's
very cool. Yeah, our curator at Griffith Observatory, Dr. Laura Danley, she was on Keck a couple months ago, and she filmed all over, and we're turning that into something that we're going to show the public. So
it was actually a requirement. So Dr. Danley's been trying to get one of the astronomers using Keck on All Space Considered for years, and he said, why would I go on your show? We have nothing to talk about. And so he said, you want me on your show? You have to come do astronomy with me. So she flew out to Hawaii, and they had some telescope time together. And so they're turning that into a little film, and he will come back. He'll come on the show to talk about that.
Yeah.
Because now they
that's a great idea.
Yeah.
Yeah. I personally was surprised by the number of snacks that were in that room. Like, holy moly.
What else do you do?
That was like that could feed a small standing army, you know? Like now I want to be an astronomer because of the snacks. So
come for the science, stay for the Kit Kats.
Boredom. You're sitting there a lot of times you have long exposure. You just drink coffee and eat snacks. You got to do something to stay awake.
How is that different? Man. So you were talking about the difference, hands-on space, hands-on at a ground-based telescope versus when you're waiting for stuff coming down from Hubble. Are there as many
Where
snacks?
they both have in common is the preparation, the proposal writing to get the time on the telescope. And that is similar for both. But when you get time on smaller ground-based telescopes, then you actually have to travel to the telescope and you go up and you're up all night, just like people imagine astronomers are. If you get your space telescope time, regardless of the platform, you'll get notified when your data is in the archive, and then you can download it from your office or wherever and work your normal hours. So it's easier, certainly, but as I say, you lose a little bit of the romance of doing astronomy.
The romance of freezing your butt off at 13,000 feet.
Yeah. You're getting an oxygen-deprived headache, all that stuff.
Yes!
Sick.
Highway to the danger zone.
Altitude sickness. Altitude sickness. Yeah, I'm just gonna. Yeah. Anyways, we are 3 minutes out.
3 minutes out.
So I guess we now have to. Let me straighten up my collar a little bit. So, have to get serious here, apparently. So.
That's a crew neck.
Mm-hmm. Yeah. By the way, I'd like to point out to Ben that my microphone has not flipped yet, so it looks like I finally have a shirt.
One.
Yeah, one shirt in my vast array of shirts, of science shirts that have it. So
I feel like the orientation of the cable is what makes the mic flip.
Yeah.
If it's like yanking, then it would go.
I feel like Dutta could run some simulations for that. Jump onto Monte Carlo and make it happen. So. Something. I was going to say, one of my favorite Twitter accounts, actually, that I follow is, I can't remember the name of it. It's like at Hubble Live or something like that. And it shows what Hubble is observing at that time and what it's observing, which instrument it's using, and who put in the proposal for it. So, and it's so cool because, the person who put in the proposal, if they have a Twitter account, it'll add their Twitter account to that. So, and it's really... It's really cool, and I guess that's one way you can get alerted that your proposal on Hubble's getting its data, so through Twitter. So
that sounds tweet.
Sarah. Oh my gosh, here we go. The puns are upon us.
Fair warning, I do pun a lot. If you feel like joining in, by all means.
Yeah, we're pretty good.
Did you feel Carrie Ann's eyes roll?
60 seconds.
Palpable. Shaking her head and mad. Not really mad. Just so disappointed. Sorry,
this is going to be a fun show. I can already tell. All right, we should be about 30 seconds out now.
Right.
We'll see how many takes.
One.
One? You think so, Ben? Ben has faith in me today.
By decree.
So, yeah, so we're going to come on this one, and we'll be good to go. So, all right, are you ready, Dr. Smith?
I'm ready.
Okay, very cool. Well, I think we're like 20 seconds away now? Something like that, so... We're coming up on it. What's up? I can't hear you, Ben. Hello, everyone, and welcome to Tomorrow, episode 12.11. And we are so glad to have you here on our show today. We've got a pretty exciting one. But before we get into that, let's introduce ourselves. My name is Jared. I'm going to be your host for episode 12.11 today. I've also got Sarah over here as well, who's going to be like, you're also a host. We're like co-hosting together,
cool.
but
Yeah.
like, it is. We have an awesome guest today. I'm super stoked about this. Been waiting all week for Dr. Eric Smith from the James Webb Space Telescope. He's the program scientist from NASA headquarters. So doesn't get much bigger than that for James Webb. And Dr. Smith, thanks for coming on the show today.
Oh, my pleasure. Always happy to talk about James Webb.
So let's go ahead and just jump right into it by sort of talking about you a little bit. Kind of what's your background with astronomy, and how did you get involved with James Webb?
My background started out as an optical astronomer. I started my research in interacting and active galaxies. So when galaxies come together and collide, they often drive matter to the centers where their black holes are, and that in turn creates some activity that we see in various forms. After I did my ground-based work, I went to the Goddard Space Flight Center, where I was a postdoctoral fellow working with Dr. Sarah Heap on some astronomy related to Hubble, but also working in the ultraviolet part of the spectrum on something called the Ultraviolet Imaging Telescope. And there again, I was looking at different types of interacting or active galaxies or clusters of galaxies. When that work was tailing down, and I was thinking, what's the next thing I want to get involved with? Dr. John Mather, who's the project scientist at Goddard for Webb, came to my office and said, hey, I'm thinking about designing a new telescope. You want to work on that with me? And I thought, well, that should be a fun activity for a few years. And 20-some years later, that's what I'm doing today. And I'm now much more interested in all the aspects of putting space missions together, and not just the science that comes out the back end of it.
So you're really diving into this project scientist role and all of the aspects of it.
Yeah, I've had many different roles on Webb. Started out as John Mather's deputy project scientist, moved to headquarters as the program scientist, was deputy program director, and always stayed the program scientist. So I've seen Webb from many different aspects, and that's been really interesting.
Very, very cool. So, before Webb, there was a proposal before it called High Z, and did that sort of end up morphing itself into Webb?
High Z was a proposal that was submitted by a man named Peter Stockman. He submitted it to NASA. He worked at the Space Telescope Science Institute, and it was largely in response to a report that NASA commissioned. That report was titled HST and Beyond, and it was the agency asking the science community, now that Hubble is repaired, what should we do next? They listed three things, one of which was build an infrared optimized space telescope. And so the High Z proposal was submitted in response to that. Ultimately, NASA headquarters, this was before I started working there, sent a letter to John Mather saying, hey, why don't you design an infrared telescope similar to High Z? And that's where Webb started. That was October of 1995, and I started March of 1996 working on the mission then.
Man.
But High Z was actually in response to the astronomical community saying we needed this kind of mission, and what became Webb grew out of that. Mm-hmm. The science is similar, the technology is very different than ultimately what was in High Z.
Gotcha. And, March of 1996, you're like right there at the straight up beginning of James Webb. Was that time period sort of like the paper napkin moment? Like this is how we're gonna do it, and this is our proposal, and this is how we're moving forward?
Sure, I can remember very well the whiteboard drawing of what was called the yardstick mission. Whenever the government is designing a flagship mission like this, it has its own design. Ultimately, you send out a request for proposals to industry, and then they propose. But the government has to make its own design to be more or less a smart buyer. And so I can remember very clearly seeing on the whiteboard the little drawing of basically what Webb looks like even today. And when I see the hardware now, and I think back to that drawing, it's like, wow, I didn't realize how complex this would become from that very simple little line drawing on the whiteboard.
Wow.
I love how your early science kind of made you the perfect fit for this particular telescope. As we look back at the early galaxies, you're going to be watching. You're going to get to see the mergers that you studied in close-up galaxies, but at the beginning of our universe.
Yeah, the type of science I used to do when I was still active, you can now trace much earlier in the history of the universe. Yeah. One of the things that will be very exciting that Webb will do, not right away because it will take a number of years to accumulate the data, but because we'll see some of the first galaxies, and of course we can look at nearby galaxies, we will be able to watch the universe build up galaxies all through cosmic time, and so obtain a complete history of galaxies and how they grew. So that's very interesting for me, and although it will take a long time for that to be accomplished, and it'll be done by young researchers today, I still really look forward to the answers.
And a lot of I think this might be a good time to clarify. A lot of our chat is asking sort of, is this a successor to Hubble? So how would you answer that? I know this is dedicated infrared, and Hubble was a wider field of frequencies.
Well, I like to describe Webb as the scientific successor to Hubble. It doesn't duplicate the wavelength coverage, as you pointed out. We're primarily near infrared to mid-infrared. We do go a little bit into the reddest parts of the spectrum that your eyes can see. But for the most part, we're studying heat radiation, infrared. We're doing that because Hubble, in looking for the early galaxies, Hubble did try that. It found that those galaxies are far enough away that the light that left them has shifted into the near-infrared part of the spectrum. So to see it, we had to build an infrared optimized telescope. So we're the scientific successor. Hubble pointed the way, and we're going to follow it up with Webb. So we can't duplicate the things that Hubble can still do even today. And next year is 30 years for Hubble. And we're still grateful that we'll be able to have them both there at the same time, but it will be able to do things that Hubble pointed the way to but couldn't quite get to because it didn't have the right kind of wavelength optimization.
So Hanny's Roarwork from our Twitch chat room, kind of to go in with the wavelengths, with infrared, is asking, will James Webb make color pictures, or will all the pictures be black and white? And I think this goes into a very interesting thing about sort of like putting out false color, if you will, so that you can interpret the data with it.
Yeah.
Yeah. So the pictures from Webb will look just like pictures from Hubble. There'll be that very sharp visual acuity to them, and we'll use different filters. They won't have names like blue, red or green filters. They'll have wavelengths associated with them in the near infrared, but you can use these multiple color filters just like you do in visual photography to colorize your photos. So, and we'll probably use the same coloring conventions where redder things in the picture are cooler and the bluer things are hotter. So the pictures will be colorized just like the ones from Hubble are, and they'll be just as sharp in their vision.
So to kind of go with James Webb here, what's like the specific goals of James Webb? Because with Hubble, there was a very clear set of goals with it. What is that set of goals with James Webb?
The primary goal for Webb was to image the first stars and galaxies to form after the Big Bang. Hubble tried that, as I alluded to, and it wasn't able to see them. They were further back in time. They were fainter, so we needed a bigger infrared telescope. So that's the primary objective. because it's a general purpose telescope with a lot of capability, we know that it's going to be doing not only this early universe science. Recently, the whole field of exoplanets has exploded, and we know that people are going to be using the spectroscopy capabilities of Webb to look at the atmospheres of nearby exoplanets to see if they might potentially be habitable. And then because we can see the earliest parts, the earliest structures that form the universe, we know people will watch the universe evolve through time, so they'll study this evolution of galaxies. And then importantly, because we're an infrared telescope, that means the light that comes to us can penetrate dust clouds in our own galaxies, which is where stars and planets form. So this telescope will be an excellent one for studying the birth of stars and galaxies. Those are just the things we know people are going to do today. Usually the most amazing thing that any observatory does is the project you haven't thought of yet today, but somebody thinks of in 3 or 4 years, and the observatory wasn't really planned for that, but that turns out to be really exciting because it's brand new.
I actually want to kind of piggyback off of this one, and it's the major function of primary mission goal of Webb is what you just said. But so your job, part of your job is safeguarding the level 1 science requirements of this mission. Could you tell us a little bit about what that was like? What kind of fights, or was it all very collaborative? What does it look like making this telescope happen over such a especially long period?
Yeah, in the beginning, you have to decide what are your must-haves for the telescope. And because we knew these early galaxy was the must-have for the mission, we had to use the best theoretical estimates at the time for how bright would these objects be, how dense would they be on the sky, and then that you turn into engineering requirements. If I know it's this faint and there's this many of them, then I have to have a telescope that's so big, and it has to be optimized for the infrared. And now that you have these engineering parameters, you have an engineering group goes off and designs it, and they'll do a cost estimate for it. And often the tension between science and reality, in some sense, comes in when that cost estimate comes in. And someone says, well, if you want this, this is how much it's going to cost. And sometimes you have to say, okay, well, I can back off a little bit on my requirement to bring down the cost. In the case of Webb, our level 1 requirements have stayed stable since the late 1990s, because this very specific goal of finding these first galaxies, that really sets a pretty hard limit on your wavelength coverage and your aperture size. And the rest of the mission sort of flows from that. So where the program scientist is very active is in the beginning of the mission, helping and getting it established, and then at the back end of the mission, as you get ready to do science, making sure the community is ready to analyze the data you get there. And we have the great advantage on Webb of being able to use the folks at the Space Telescope Science Institute, just like we did on Hubble. So they're going gangbusters, and I have no doubt that the community will be ready to hit the ground running for Webb.
Nice.
Very cool.
Yeah. So talking about some of the things you have to put together, what were some of the biggest challenges working with the James Webb Space Telescope? Because this is going to be the largest infrared telescope and also the largest telescope anybody's put into space as well.
Yeah. We had challenges in I'll say a couple of arenas. There's the obvious technical challenge of making something that's this big and it has to fold up to fit inside a rocket shroud. And that one is, people can understand that pretty easily. Here you have a telescope that's 6.5 meters, more than 21 feet wide. It's got to fit inside a 5-meter shroud. So it has to fold up. And because it's an infrared telescope, we want it to be very cold. We want it to be colder than the signatures we're looking for. If your telescope is warm and you're looking for heat, it's like trying to observe while shining a flashlight right in your eye. So we have to have it very cold and very large and deployable. And so those give us very stringent technical requirements. Things have to be able to work while they're very cold, where material properties are completely different and non-intuitive. At Webb's temperature, everything but helium is a solid. So when you are building something like this, the other challenge that comes in are collaborative or management challenges. We partner with international space agencies on almost all large NASA missions, and Webb is no different. We're partnered with the European Space Agency and the Canadian Space Agency. And at the beginning, you have to do the elaborate dance where you find out what your partners want to contribute. Do you want that? Is it useful? In addition to the fun stuff, they want to give you science instruments for their science community. You want to get some functional things from them as well. So there's that negotiation. And sometimes the people part of it is harder than the technical part, because the technical part just obeys the laws of physics. The people part, well, that's more complicated.
I like that people are more complicated than physics.
Right.
So it's a good way to describe it. So
there aren't a whole lot of algorithms to. Never mind. Just kidding. All right. Must abort that statement. But that actually, so your comments actually brought up, give me a good in for Hanny's Vorwarp from Twitch. And being an infrared telescope, is there any chance of JWST lasting as long as Hubble, or will it run out of coolant long before then?
Great question. Webb uses two ways to cool its instruments. One is passive cooling. So all the near-infrared instruments are cooled just by the telescope radiating heat to space. So we don't run out of coolant for them. And on the mid-infrared instrument, which we do need to cool the detector to 6 Kelvin, 6 degrees above absolute zero, we have a little refrigerator system. So it's a closed system, so we don't run out of coolant there. The life-limiting aspect of Webb is the fuel that we use for station keeping. As we orbit about the second Lagrange point, and we use our reaction wheels to turn the spacecraft, we sometimes have to use propellant to what's called desaturate those wheels, push against something to take the spin out of those wheels, and that propellant will eventually run out. Now, we've sized it for 10 years. If we get a very precise launch to our L2 orbit, we might get a little more. And I think as people learn how to operate the telescope better, they'll learn to conserve fuel. So I anticipate we'll get somewhere between 10 and 15 years out of Webb, but eventually we will run out of fuel.
yeah, and Adam Smith on YouTube is actually asking, why is James Webb going to orbit in a Lagrange point?
That's because we're an infrared telescope, and you want to get away from sources of heat when you're in space. And if you were in a low Earth orbit, like Hubble or most telescopes, then you are very close. You're 300 miles away from a giant infrared source, the Earth. And by going to the second Lagrange point, which is roughly 1 million miles away from Earth, you can arrange to follow the Earth around the sun in its orbit, and you can keep the Earth, the sun, and the moon roughly at the same point in the sky behind you. So you can have, like Webb, a sun shield on one side that looks back towards the sun, Earth, and moon, rather than a tube that most telescopes use, and that saves you mass. And so you can put that mass that would have otherwise been in a tube into things like science instruments or telescope mirrors.
So, yeah, just to kind of talk about saving mass, just real quick, how much does James Webb weigh versus how much does Hubble weigh?
Webb is about 1/2 the mass of Hubble. So there's where you can see technology advancing. We have very lightweight structures, both in our mirror and the things that hold the mirror. And we needed these lightweight structures so that we could, again, put the mass into things that we wanted, which is mirror area and science instruments. In the case of Hubble, they didn't really need to be so mass constrained. So they were, again, about twice the mass of what Webb is.
Okay. So Dave Anderson from YouTube was wondering if JWST is going to be the first instrument to occupy L2. Or are you going to have company out there?
There are actually several other satellites that have gone there, both U.S. and some from the European Space Agency. It's actually a great place to put space telescopes because it's a very benign environment. You don't have the debris that's associated with low Earth orbit. There's a lot of stuff floating around out there now. L2 is a place that you really orbit about. It's not a single location. So there's an enormous region of space where you can orbit, and therefore you're not really worried about running into anything. And the thermal environment, again, is very benign. It's very constant temperature. So it's a good place to put space telescopes.
And Rebel in our chat room has a really interesting question, which is James Webb a larger project than Hubble was at its time, or is it more clear-cut because we know more engineering-wise and astronomical-wise? And I guess kind of just to piggyback on that a little bit, what lessons has James Webb applied to itself that have been learned from previous space telescopes?
As far as the project size, I think they're probably comparable. I don't know what the staffing levels were back in the late 70s, early 80s when Hubble was being built up. When Webb was at its peak, there was about 2,000 people or so working on the program. Now I think we're probably around half of that. So in size of the number of people working on it, probably comparable. As far as what lessons learned, you're always learning lessons from previous missions. And one of the ones that we learned from Hubble was that you need to test your mirror in a different way, and even better, at a different facility from where you made the mirror. Everyone recalls that when Hubble was built, it had this problem that the mirror was made perfectly, but perfectly out of focus. And that was because the test for the focus was made at the same facility that made the mirror. And it was the facility itself that contained the error. And so we knew that when we built up the mirror for Webb, we needed to test it in a different way, in a different place than when we manufactured it. And we did that, and we verified, actually a couple summers ago, that the telescope mirror works exactly as planned, and it will, all these 18 mirror segments will function like one when it gets into space.
Nice. That's good.
Sort of on that, we've got a question from Elias1981 on YouTube. Can it be refueled in orbit? It's going to an L2, so with Hubble's vision issues, it was great that it was in orbit around Earth, but James Webb is kind of going to be on its own out at L2. Is there anything that we can do to either refuel it or fix any errors that happen out there?
Well, let's see. I'll talk first about how did we design in I'll say redundancy or tolerance, because we knew from the start we weren't going to be able to repair it. If you think back to the time when this was being designed, this was the late 90s, in the earliest design phases. The way that people got into space then was either via Soyuz or space shuttle. We knew that those were both low Earth orbit vehicles, and we were going to L2, so there was no imagining that there would be any astronaut servicing for Webb. The telescope is complex enough and the system's distributed in a way that precludes the easy instrument replacement that Hubble had. If you remember seeing the astronauts taking those instruments, they sort of slid them out and in because they were self-contained. In the case of Webb, a lot of the functionality is distributed through the structure, and so you can't just take one instrument out and put another one in the same way. So therefore, we had to design in a lot of redundancy in the moving parts so that we had more than one way to address an actuator electrically. And the mirrors themselves, we know we can push and pull on them. We can tip and tilt them. We can even press on the center of them, flatten them, or let them curve more. So we built in adjustability knowing that we wouldn't be able to go up and fix it. Now, the question on refueling is an interesting one. We don't currently have the capability to refuel Webb, but as we're finishing up the spacecraft, we want to make sure that we don't preclude some future capability from going to do that. So there are targets on the bottom of Webb, the pieces that attach to the rocket, optical targets, just like you've seen when things come up to the space station. They have these black and white targets that cameras can look at. We have those, and the fuel ports are on the bottom. So if someday there's a robotic mission that could fuel Webb, we want to be able to take advantage of it. We just don't have that in our plans right now.
Yeah, well, there you
Fantastic.
go. Yeah, that's awesome. So hearing about all of that, when you were talking about being able to move the mirrors that way, I literally just like my face exploded.
There was I wanted to ask actually kind of piggybacking on that. So some of the research I was doing into, the tech on board, one of the advancements that has come out of this already is some of the work on adapting the mirrors, being able to flex them, and the algorithms used to make sure that everything is precisely positioned. They've already been used to aid in diagnosing human eye variances and improving LASIK surgery. Is there anything else that has come out of this James Webb Telescope already that we don't know about?
Well, that's probably the one that has the widest applicability to everybody who's going to have LASIK surgery. The need to measure our own optics very precisely was what generated this. It's an interferometer, it's called, that can measure very precisely optical surfaces. I know that as various components for Webb were being manufactured, and because of our thermal requirements, we need to be very cold. We have a lot of structures made out of graphite material, sheets of graphite that are glued together. So they become very stiff and rigid at cold temperatures, but they're very lightweight. And how those are put together, sometimes they're just glued together. And the companies that make these parts had to come up with new ways to bond and glue these together for our requirements. But then they realized, this is actually a better way to do these bonds for everything. So sometimes the improvements are in manufacturing techniques that don't get such wide public recognition, but they do help U.S. industry. So we look for, everybody thinks of the spin-offs that are publicly recognizable, but a lot of times they're in manufacturing and they benefit us in ways that aren't quite so direct.
Very cool.
Yeah, and Loopy in our chat room is asking about, these advances for adaptive optics, maybe for ground-based telescopes as well, with the ability to move those mirrors as finely as you can.
That's right. And ground-based telescopes use similar technologies. In fact, they often now, in some of the ground-based work for exoplanet research, they rely on smaller mirrors in the system, not the big giant ones, but those mirrors are called deformable because they have many actuators behind them that can push and pull on the whole surface to make it move very rapidly as well. They need to do that in response to how the atmosphere is changing light when the light from stars comes through the atmosphere. We don't need to move very rapidly. We'll probably only be adjusting Webb on the weeks or months time scale as the mirrors change their shape in response to different temperatures. As the telescope is illuminated from behind a little differently, not the telescope, but the sun shield is illuminated by the sun, it will introduce slight temperature changes in the mirrors, and we'll have to take those out by moving the mirrors around.
So Luc S. Van Hout from YouTube has two really good questions that I kind of want to throw in there, which is, what is the volume difference between Webb and Hubble? And I assume the volume, assume that being like both size and also, let's say, mirror as well. And they're also asking, how much power does the James Webb Space Telescope use when fully operational?
It uses 2 kilowatts is the power. So it's actually... it's a sizable amount of power, but not compared to larger commercial spacecraft. So our power requirements aren't that great. As far as the volume, it's a little difficult to compare because Hubble is this, more or less traditional, a tube-like telescope, and we have this sun shield, and then the telescope sticks out of it, and of course, then it looks in one direction like that. So I'm not sure if you would want to include the volume of the whole James Webb area. Perhaps it's best just to compare the mirror sizes. Hubble's mirror is 2.4 meters in diameter, and ours is 6.5 meters in diameter. So there's a factor of 7 in area of mirror. And we not only use that factor of 7 gives us an advantage, we have advanced, more sensitive detectors. And because we're in a place that we're not going in and out of the Earth's shadow every 90 minutes, we can observe constantly. And so those 3 things give us a greater observing efficiency. Sometimes you'll see the phrase bandied about 100 times more powerful than Hubble. It's some multiplication of those 3 factors that give you that.
And Henny's Vorwerp in Twitch has a question, which I'm sure a lot of people have, which is, how confident are you about the origami unfolding of the telescope? So if you could tell us a little bit about, how you have to prepare Webb for launch. And also in our chat room from YouTube, Racer X Ninyab is asking, why not launch on a Falcon Heavy? And I know that's thrown out all the time now, and I personally know the reason as to why you can't launch it on a Falcon Heavy. But if maybe you want to take on why the specific rocket that James Webb is flying on was chosen, and the preparations that you're going to have to do, because launch is technically 2 years exactly to this day that we're shooting it on March 30th. So if you want to tell us a little bit about that, go for it.
Okay, so first I'll start with the origami aspect of it. We practice the folding and unfolding of the telescope a lot on the ground. In fact, that's the stage. We're in the integration and test phase right now, where we will articulate the telescope on the ground just as it will be in space. So we have to build very elaborate gravity offloading systems, because when the telescope's unfolding in space, it's unfolding in 0 gravity. And the structures are built to operate in 0 gravity. So we can't operate them that way on Earth. So we have to build something that counteracts their own weight. And so you saw a little video earlier of that secondary mirror tower coming out. We lay the telescope on its side and actuate that. And we've folded the drop leaf table sides of the mirrors up. We've actuated the mirrors, and they have practiced numerous times folding and unfolding the sun shield. And as you can imagine, that's the most complex of all of them, because there are 5 layers to this sun shield. Each layer is about the thickness of a plastic baggie, and it's roughly the size of a tennis court. And that has to be unfolded and then very precisely separated from one another, so there's space between them. And then they have to fold it back up again. And as they fold it, the layers are folded sort of back and forth over one another, these 5 layers, and then they must all line up, and then they must be held down during launch by a pin. There's about 109 pins that go through this sun shield to hold it in place during launch. And then when it unfolds, all those holes can't line up because you can't let light through. So they have to be offset from one another when it's unfolded. So the origami aspect of it is, that was a great engineering problem, and it's one that we will just practice to make sure that it works in space. Now, as far as the launch vehicle, when we were setting up the collaboration with, in this case, the European Space Agency, they wanted to provide us science instruments, and we wanted them to, because they build good science instruments. But we also wanted something on the more functional side. And we looked at various components of the spacecraft or operations. But in the end, what they had that was the most value to us and was the simplest technical interface was a ride on the Ariane 5 rocket. And the ESA's Ariane 5, built by Arianespace, is actually the most successful rocket in the world for its weight class. So we're riding the safest ride we have to space. And when our mission was designed, we had to use the vibration and acoustic spectrum of the Ariane 5. And so we're designed for that. If we had to design for something different, then we'd have to do all kinds of testing all over again for different acoustics and vibration environments.
So, Splodin from our YouTube chat, nice name there. So we've already talked about the first part of their question, which is, what is your confidence level for a successful launch? But they have a second part of their question, which is there a backup plan? So I guess sort of like, do you have contingencies? Like, let's say the upper stage of the Ariane 5 has like a hydrogen leak somewhere, and they burn through their the amount they have in reserve, and it doesn't quite put James Webb on a trajectory to L2. Do you have sort of like backup contingencies for things like that?
Well, we would have to use some of our own fuel then to get us into the proper orbit. And what that would do is it just reduce the mission lifetime. If we have to use a lot of our fuel, then we take away the fuel that we would have used for station keeping later on. In the case of planning for contingencies, once we're released from the Ariane upper stage, that's what's going on right now at the Space Telescope Science Institute, where the mission will be operated as well. They are already practicing, we'll rehearse the mid-course correction burn, and then they'll throw in an anomaly and say, well, it didn't work quite right. What do you have to do now to get it back? Or we're going to turn on our instrument. Oh, it didn't turn on the way you think. So they practice getting it to turn on in a different way. So planning for these kind of contingencies is something that every NASA mission does, and we're doing it just the same way on Webb too.
Very, very cool. And kind of, the name James Webb.
Yeah.
Who's James Webb? Because we know Edwin Hubble, especially us, who work at Griffith Observatory, because he did his work locally here in the Los Angeles area at Mount Wilson Observatory, and basically we like to say discovered the universe. So we know about Hubble, but who is James Webb, and like why is he special enough to get this space telescope named after him?
Yeah, this is a question that we get a lot of times, and it's actually a very reasonable one, because James Webb was the second NASA administrator, but he was the man who designed the Apollo program. And if you think about it, this was a program that went from the early 60s to successfully landing on the moon by 1969. Just an astounding feat, going from almost no space program to landing on the moon in less than 10 years. And that whole enterprise was put together by Webb. Webb was actually a lawyer by training, so not a scientist, not an engineer. He was a master at making the government work. And that is something that the space program actually needs. We have lots of talented scientists and engineers, but sometimes you need management to get it to work. Okay, so Webb was a good guy for getting the Apollo program. Why is a science mission named after him? Webb realized that to get the Apollo program to work on the time scale that President Kennedy asked him, he needed to have the best scientists and engineers he could get his hand on. And to have the best there, he had to allow them to do their own research as well. Research was a critical part of reducing risk for this incredible Apollo mission. And so Kennedy would have just been happy to say, look, we're going to the moon, get some people on the moon, scrap the rest of it. Webb recognized, no, I need to have science in my agency if you want me to do this engineering feat. And so the reason the telescope is named after him is in part because the reason we do science at NASA is somewhat attributable to the fact that James Webb was an administrator.
Wow, yeah. So very, very cool that we got that named after him. So, yeah. So those of you who didn't know who James Webb is, now you know who James Webb is. So if you're a big fan of Apollo, he's the guy.
And who isn't?
Yeah. I mean,
50th anniversary.
Yeah, coming up on it. So.
There's actually a pretty good book. It's a small book. You probably have to go to a largish library. Probably can get it on Amazon, called Powering Apollo. And it's a biography of James Webb. And it's a pretty interesting read to read about his background and how he put the whole Apollo program together.
Very cool. So Raj Luthra in our YouTube channel is asking about the data that gets collected by James Webb. Is that going to be shared internationally? And I would assume it is. And I think even some of the instruments on board are international as well.
That's right. We have 4 science instruments on Webb. One, the near-infrared camera, or NIRCam, is built by the University of Arizona and Lockheed Martin. Dr. Marcia Ricci is the principal investigator, so that's a U.S.-only instrument. There's the near-infrared spectrograph that's provided by the European Space Agency with components from the Goddard Space Flight Center. There's the mid-infrared instrument, or MIRI. That's a collaboration of about 13 countries in Europe and the Jet Propulsion Laboratory. And then we have what's called the near-infrared imager and slitless spectrograph, and that comes from the Canadian Space Agency. So we have an international suite of instruments, and just like Hubble, people all over the world can submit proposals. They'll be peer-reviewed, and once the data come back, they either become public immediately, or sometimes astronomers elect to analyze the data for 1 year in an exclusive use period, and then it's all public after that. So everything that Webb looks at is public eventually, if not immediately.
All right. And Henny Zvorwerp on Twitch is asking, how does someone book time on James Webb? Because if I recall correctly, there was actually some time on Hubble set aside for people who were not professional scientists or researchers to work on it. And also, if I remember very early on, I can't recall the name of who's the director of the Space Telescope Institute, but he actually gave some of his own time that he gets
discretionary.
Yeah, director's discretionary time to public proposals as well to make that happen. So, is there something similar going to be for James Webb, and what's that process like to do that?
Well, there'll be a call once a year, just like Hubble, for anyone who wants to submit a proposal to the Space Telescope Science Institute, where it would get reviewed. Now, just like Hubble, the director of the Space Telescope Science Institute will have director's discretionary time that he, in this case, could dedicate to anything he wants. They've already done that for the first year. He created a program that's called the Early Release Science Program, and these are a wide range. It's a wide-ranging program. There are 13 investigations looking at almost a panoply of astrophysical phenomena, and all those data become public immediately, so that people proposing for the second round will have Webb data to work on to get their hands dirty, so to speak, so they know how to write even better proposals the second time. Whether there's any time set aside for, say, amateur astronomers or some public interest, that's TBD yet.
So Karthik Naran, NKKN, in our YouTube chat is asking, what will be the first discovery from James Webb? And I kind of want to sort of rephrase that a little bit, which is, what are some of the first things that we're expecting from James Webb? Is there things already scheduled and lined up that are planned for James Webb in its initial, maybe during like its calibration period or even during that first run with it?
Yeah, I actually was wondering, what is the first thing you plan to aim that telescope at?
Well, I can tell you the first thing we'll look at is probably, I'll say a single star, but a small star field that we'll use to focus the telescope. Now, in the case of Hubble or most telescopes, you want that first picture to be perfect. We know that the first picture from Webb will be 18 or so fuzzy blobs because those 18 mirror segments won't be phased perfectly. Right. That first picture will be these blobs, and then they'll start moving the mirrors segments around, and they'll bring it all to focus. So eventually there'll be a sharply focused star. But the first picture will be probably 18 fuzzy blobs or something like that. But we do have people who are called guaranteed time observers. They've been working with us since 2002. to help define the science of the mission. Their targets are already planned for the first year. And this early release science program is also planned. You could read about the early release science if you went to the Space Telescope Science Institute's website, and or if you just Googled JWST early release science, you can see the list of these 13 programs, and they range from looking at very hot nearby stars to looking at the deep universe. So already we can see that Webb is going to be doing a lot of things in its first year, from looking for those early galaxies to looking at atmospheres of nearby exoplanets, and also studying things in the outer solar system, moons of Neptune and Uranus, most likely.
Very cool. Yeah. Well, very cool objects, I was going to say, with that right there. So talking, sort of like going back a little bit to sort of like administration and things like they had with James Webb, the namesake, with that, there were some sort of like schedule and budgetary things that happened with the telescope, which sort of the exact same stuff happened with Hubble during its development as well. Were those sort of similar to each other, or were there sort of unique things to James Webb that caused, the schedule delays and the budgetary increase with it, and it's like exclusive to Webb as opposed to what Hubble went through?
I wasn't around when Hubble was going through some of its issues, but I think many of those were related to the serviceability of the mission, because similar technologies for telescopes had been built for other government agencies. In the case of Webb, some of our delays came early on from how the mission was funded. And that was, there wasn't sufficient funding laid in early on, so that if a problem was determined to arise, I need more money to do something this year. Well, if you don't have that money, then you postpone it, you push it out into the future, and that eventually causes a delay. Another area where Webb experienced delays was just in the sheer technical challenge of doing this one-of-a-kind, first-of-a-kind telescope. Unlike many other space missions, we couldn't rely on anyone having built anything like this before, and so we're learning what it takes to build a large articulated cryogenic structure in space. And those technical challenges were the primary cause for the most recent delay, and we just need to make sure that we finish integrating and testing everything, having now essentially built it all to be in just two pieces: the telescope and science instruments, which have completed their testing and are ready to go, and the spacecraft and sunshield, which are undergoing their testing before we put the two pieces together.
Oh, man. Okay, I have to ask, where is the telescope right now? We know it's gone through vibration testing, and it's being, well, where is it right now?
The telescope right now is in Redondo Beach, California. So if you got in your car or you got in the plane and you went down south, you could see it at the Northrop Grumman facilities there in what they call Space Park.
Oh my gosh.
I think we just planned a road trip.
Yeah, I think we can literally drive like 30 minutes right now and go get it real quick. So
you can get us in, right?
Oh, sure. Yeah, you can see the telescope sitting in a big clean room. The spacecraft is just about ready to undergo what we call its thermal vacuum testing. So it's already been blasted with sound waves like would come from the rocket, and they put it on the vibration tables and they've shaken it, and they're about to put it in the thermal vacuum chamber down there in Space Park. So that's where all the hardware is right now. It's in Southern California.
So what's it like to work on a project like this? Because this is a flagship mission. These are the types of missions that end up changing our fundamental understanding of the universe. What is it like to be a part of that?
It's an incredible privilege, first off, to work with the people who make missions like this possible. There are so many talented scientists, engineers, managers, resources people, budget people, legal teams, that look into both U.S. and international law. The most fun for me is just getting to work with all these very dedicated people. And I think that this flagship type mission really draws out people who are willing to dedicate a substantial fraction of their career to it. And it's that dedication, the shared mission, that is the thing I'll always remember the most from Webb. That and the crazy things we've all done over the past 20 years to put it together.
So what has been your favorite moment working on James Webb? Because you've been on Webb since the beginning, March 1996. What has been your absolute favorite moment so far working on Webb?
I think it was seeing the telescope when it was finally put together and raised up in the clean room at the Goddard Space Flight Center. And I think I might have seen a little clip of it go by there. And to stand in, there's a big window you could stand and see yourself reflected in that mirror. That was really a cool moment to think of all the work that's gone in from all these people, and to stand there and to see yourself reflected in their work was, it was moving.
That's so great. I would love to know if way back in 1996, did you have any idea what you were getting yourself into?
Obviously not.
Would you change any of
it? Everything I had worked on were, in retrospect now, small projects. But I did see other people who had worked a long time on Hubble there at Goddard. And I saw the camaraderie, the pride they felt in Hubble. And so I knew, these big missions, there must be something to them because a lot of people here really love them. And now having worked on Webb, I understand the same feelings they had for Hubble, I have for Webb. But yeah, I didn't imagine it was going to be this long, but it has been fun.
And Dr. Smith, human spaceflight excites everybody. It's very difficult to find anyone who's not excited about it. Yeah. But with astronomy, folks like us on the show are very excited about it. So for the folks who may not have that same level of excitement, why should they feel excited about a mission like James Webb? What is that special thing that James Webb is doing for us?
Well, I like to think of Webb as NASA's deepest space exploration. Now, we're an agency that explores space. We use humans to explore local space. We send robots to nearby planets to explore them, and we use telescopes to explore even farther. And so each of those is an expression of human curiosity. Eventually, we'll push people out farther than they've gone today. We'll push our robotic missions out farther than they've gone today. There are some places in the universe where we can only go via telescopes. And that's always been my pitch to people who understand the human side of spaceflight, or the human part of NASA and its benefits. And I say that same curiosity is what we're carrying just to the places where we won't ever be able to send humans in person.
All right. And Dr. Eric Smith, thank you so much for coming on the show today. Program scientist from the James Webb Space Telescope. Thanks again for coming on and having this awesome discussion with us today about a telescope that is going to be unbelievable with it. So.
Well, thank you very much for having me, and thanks to your viewers for their great questions. I really enjoyed them.
Excellent. All right. And of course, our viewers, we want to thank our viewers because this show is brought to us by our viewers. Our patrons and the folks who give us their time working on our projects and everything, we really genuinely would not be able to do this without you folks. And we always say that, we wouldn't be able to do it without you, but we really wouldn't. We wouldn't be able to get stories like from Dr. Eric Smith here out to the world, we wouldn't be able to have you sort of, I guess, have access, if you will, to these folks. And that's pretty unique to me. And I can't really think of anyone else who's doing something like this. And we're doing this because you help us enable us to do this. So it's incredibly important to have your support. And we are ever thankful and ever grateful for your support here at TMRO. So thank you so much. And I guess that's going to wrap up our show for today. So thanks so much for tuning in, and have fun out there exploring the universe. So see you later.
Mayhem ensues.
All right, now the mayhem begins.
All right. Where do we even begin?
Chris asked, is it just me or is it a short show today? No, we're back to our original show times of around 42 minutes.
Yeah.
Yes.
Yeah. Also, it was really freaking interesting, so it did not feel like nearly an hour-long interview, right?
Yes. Thank you so much,
Yeah,
Dr.
thank
Smith.
you, Dr. Smith. This is awesome.
So excited.
My pleasure. I see I got mine nested where you couldn't quite see it on the camera.
Oh, dang, there you go.
Meatball, matching meatballs.
Y'all got that memo. I didn't.
SDO, though. I had to make this. I was like, nah.
I did not. I have astronomers
you do.
on here. I have Hipparchus, Copernicus, Galileo, Kepler, Newton, and Herschel. So, bye, kitty. So, yeah, that's what's up. So.
And there is a link between all 6 of those astronomers.
Yes, there is.
They're monumented.
Yeah, they're
the
part of our
Griffith
monument at
Observatory.
Griffith. Yeah. So, although I think we need to throw some more up there.
Yeah.
So,
I agree.
don't know who I'd throw up there. So.
We could have a whole other monument.
Yeah, we should. I think because if we have
Monument 2.0.
we have a monument for James Dean at the observatory.
That one wasn't our fault.
That's true. So I like how you phrased that.
Yeah,
That's
that was
pretty good.
intentional.
So, yeah.
The artist who sculpted that was working on it when Dean
crashed.
Went to that, the eternal pit stop. And
well, I guess that's appropriate for him.
So he held on to that bust for years, and then eventually was like, you know what, Griffith Observatory, can you do something with it? And so we put it out there.
Very nice.
Have you actually, Dr. Smith, have you been to Griffith Observatory?
I was out there for the first time last fall and actually talked with Laura when I was out there. And that's when she recruited me to come in January, but then, the circumstances being what they may. Right. So it was, I've always loved the building of Griffith Observatory. And so it was fun to finally get to come out there and see it.
Nice.
Well, looking forward to when you can come back.
Yeah, I'm out there I'm down at Redondo Beach every month, but I don't make it all the way up there typically. Although this past month, I did get to go with some friends to visit the Magic Castle there. That was very cool.
You got into the Magic Castle.
Oh, that's cool.
Pretty awesome.
Yeah.
I've never been to the Magic Castle.
I've done a thing Ben hasn't?
Yeah.
What?
How'd you like the Magic Castle?
It was phenomenal. I've always liked magic. When I was growing up, guy across the street was a professional magician and was a member of the Magic Castle. I was friends with his son. And so, I heard about it then. This was in Pennsylvania. And so to finally get to go and see people, they're inches from you doing these, making cards appear, disappear, just outstanding, really fun.
Yeah.
Yeah, I'm glad I'm not the only person who's like fascinated by magic. So
I used to make their membership cards.
You used to make their membership cards? Oh, well, why didn't you make yourself one? Or did you make yourself one?
Or did they disappear?
I may or may not have.
Thanks, Dana.
Oh,
Oh
man.
boy, yeah.
Okay, I got to ask.
What else? Well, go ahead.
I was going back to the Magic Castle.
Well, I was going to ask what other cool things you do here in California if you're here often, but Magic Castle is fun too.
Did you go into the phone booth?
I did go in the phone booth, saw what you see when you go in the phone booth,
Yep.
yeah.
Nice.
That's my favorite bit.
Magic Castle, I don't know what that is.
Yeah, I don't know what it is to either.
Much
but
like
it
your socks,
sounds
and everybody
like...
who's not been, not today's socks, but the special socks.
Oh, yes, the
Yep.
special
Yeah,
socks.
The special
Yep.
socks.
Yeah. Usually when I'm out on the West Coast, it's just for a review. So you sort of, you fly in one day, you fly out a couple days later.
Right.
They used to be much longer, but now because we're in this phase where, again, most of the hardware is put together, they're relatively brief. And so it's just kind of a hit and run thing to Redondo Beach.
So most of it's put together. Why the 2-year latency at this point?
It's just the complexity of the test and final integration. Because of it takes about 4 months to unfold and refold. So each time you do that activity, that's just how long it takes. And then if there's an anomaly, that adds a little time. That's the other lesson from web, is that at some point the system just gets so complex that it's almost not a linear addition of time to do things. Things go up much quicker, and I think we're really experiencing that on web.
Gotcha.
Yeah.
Do you have nightmares of that sun shield
Oh
unfolding?
my gosh, Sarah.
I don't know how you sleep. Your cortisol levels must be through the roof at all times. Just
Well, now's the time to worry about it. People ask, will you be nervous at launch? And I actually won't be, because by then, it's already sealed in the system in some sense. So now's the time to be nervous. Is it working right? If something doesn't work as planned, then you almost have to stop and say, why didn't it go like I thought it was? Because I need to make sure I understand every piece of it. When I understand, or when we understand every piece of it, then you let it go and you're pretty confident. So nervous now, not so much when it launches.
Mm-hmm. Yeah, and someone in our chat room kind of made a little joke that Curiosity had to deal with the 7 minutes of terror, right. But James Webb is going to have to deal with 30 days of terror. Yeah. So,
yeah, we've been looking for that was it's famous within the agency, that 7 minutes of terror movie. Nothing really captured for the public and even others within the government of just how tough that was. And because our things are drawn out over a month, actually 2 weeks for the deployments, and if you actually watch them in real time, it's like watching grass grow. They're kind of slow. We haven't been able to think up a nice way to convey to the public the risk associated with it.
Yeah.
Yeah.
Yowza.
Yeah, right.
Well, if it doesn't work, you just fly another one, right?
Yeah, the second one that was built.
Yeah.
Yeah.
For a younger person. Yeah.
Yeah, we've got you guys have got 4 or 5 spares, I'm sure.
Yeah.
So.
You got a selfie stick out there just watching the deployment happen.
Hard.
You do just time lapse it.
Yeah, and how are you going to know about the deployments? Is that something that the telescope's just going to ping you back and be like, "Hey, I've done it"? Or is there
I did
a thing.
Images?
That needs to be the command that comes back. It needs to say, "I did a thing."
We say that the telescope, we don't have cameras on board to watch it, but there are sensors all throughout the telescope. So we can say that the telescope feels its deployment. You can say when the booms have come out. It feels each part as it goes out. So we'll know where things are. And one of the things we're looking at doing, sort of to engage the serious amateur astronomy or the small university community, when we're going through the sunshield deployment, is to have them do relative photometry on Webb, because we'll be a point source. But as the sunshield expands, we'll grow in brightness.
Oh.
And they'll be able to say, you, according to my measurements, you're now 50% deployed, because that's what I calculate your brightness should be.
Nice. What magnitude will Webb be at?
Right?
Because maybe I'll hunt it from my backyard.
As the depth of the iridium happens.
So, yeah.
It'll be pretty faint, sort of like the brightness of Pluto. So
never mind.
You'll want to have a serious telescope.
Never mind. My biggest telescope is 6 inches, so I'm not
womp womp.
unable to do that.
Well, 6.5 meters. Webb's got you beat.
I was going to say a little bit there. So
So when you're not doing web and you're not heading to California and going to the Magic Castle, jealous by the way, what do you do in your spare time? What do you do for fun?
What do I do for fun? Well, I've been making wine now for 8 years from California grapes, actually.
Whoa.
We get them brought here to the East Coast, and I made some for Webb's launch, made about 1,000 bottles of wine from Napa grapes.
Wow.
Oh my God, that's awesome.
So I've been doing that.
Did you
For
crush them
several
with your
years.
own feet?
Say again?
Did you crush them with your own feet? I Love Lucy style?
No, we have a machine that does that here, but they come in the pallets and we throw them into the machine.
I'm going to imagine you doing it anyway, though.
I think you just broke the internet with the you made wine for the James Webb Space Telescope launch, and now I want
Alcohol.
for every major project there needs to be some alcoholic beverage that is made en masse for that project. That'd be
Because
awesome.
James Webb is a telescope and it does spectroscopy, it might actually find alcohol out there in space for all we know.
fair.
Excuse me, ethanol. So, with that. So.
The aliens have produced a fine Cabernet on their planet, apparently.
Yeah, and as Vax said, it's 1,000 bottles that boggled them. You made 1,000 bottles of wine.
Everything is big on Webb.
That's where the budget went.
This is terrible. This is terrible, but I'm going to put it up anyhow. It says, Loopy says, so does that mean the more James Webb delays, the more mature the wine gets?
Is that the secret?
That is an unfortunate benefit of the delay.
Oh boy,
God.
this is a good one.
Well, I'm done. I feel like I've peaked. I can't. I never got to do it. By the way, hi, I'm Ben. I'm the executive producer for the show. I think you only worked with Lisa on this particular one. I never said hi, but hi.
Oh, okay. Hi, Ben.
And this needs to be said as well.
Which
Ben is magic, and he thinks he's a space princess.
Oh, I have a tiara. That's
Yes.
true.
Yeah.
Yes.
Yep.
Yeah.
All right, I think that's kind of wrapping it up
All
for
right.
us, unless you guys
Yeah,
have anything.
I can't think of 1,000 bottles of wine. So
Yeah.
that's kind of tough to beat
unless
that.
we do the song.
And
God.
actually,
1,000
tomorrow I'm
bottles of
going to
wine on the
bottle the
wall.
last barrel of it. So
What?
Say that again. I'm sorry.
tomorrow we're putting the last roughly 250 bottles into bottles from the barrel tomorrow.
Nice.
Oh, that's awesome.
Oh, man.
Congratulations.
Yeah.
So
Oh, that's really.
Oh,
do you have,
thanks, yeah.
Well, I struck gold with that one. Do you have any
Yeah,
other hobbies
right?
other than bottling wine that you do, or is that pretty much absorb James Webb and the wine absorb all your time?
Let's see. I've been playing softball at Goddard on the same team for 29 years. That's the other
Nice.
thing I do.
what position?
So it's the one thing that I've been doing at NASA longer than Webb.
Awesome.
Nice. Nice. Do you is there like does Goddard have like its own softball league, or do you guys go out and you're
So it's
local?
interesting. It used to be, you can see how the popularity of sports are changing. When I started playing, they played 4 nights a week. They had 10 teams each night, and now they're just down to 2 nights a week. So I think younger kids, they're playing soccer, lacrosse, or whatnot. But there's now just 2 leagues. There's what I call it the scientist and old guys league, and then the young everybody hits a home run league. So those are the 2 nights.
Do you guys ever go out to like softball like championships? And you're like, yeah, this is the astronomers team. We're here to knock you out, or something. I don't know
Right.
what. I don't know what. It would be intimidating.
We're going to calculate your vectors.
Yeah.
Our team won one year, but we just play within the Goddard League there. I played when I was much younger in some of the county leagues, and the people that play there they're just morphologically different. They're much bigger and stronger, and we wouldn't compete well against them.
Oh, man. Thank you so much.
Yeah, I think this was a great day. Thank you so much
My
for your
pleasure.
time. We'll have this posted within a day or two. It was a very awesome and compelling interview. Thank you so much.
Yeah, thank you for coming on.
Okay, well, my pleasure, and thank you for the invitation. I really enjoyed it, and great questions from your folks.
And thank you for just answering so freely and openly. Sometimes it can be a little like dentistry, but you just you're just a lovely person to talk with. So thank you.
Yeah.
Well, thank you, and I look forward to seeing you when I get out to Griffith in September.
Definitely. Yeah.
Absolutely.
We'll say hello for sure. So.
Yeah.
If you want a Disneyland trip, let us know.
All right, bye-bye. I'll sign off.
See you, everyone. Bye.
Bye.
Bye-bye.
Bye, everybody.